Welcome to e-learning. This time it's about U-value. Let's take a look at the problem we have to do today, because we have to find the heat transmission. And in order to find the heat transmission, we find the U-value first. And the building component is a single glazed window. We are giving the thickness of the glass. It is 2 mm. What you also must be aware of is the design temperatures, and those are given as in DS 418. The thermal conductivity can be looked up in tables. To help us do the problem, there's a manual, and today we're only using the first 4 packages. So what we have to do first is to find the resistance, and that is the thickness of the glass divided by thermal conductivity. The next thing we have to do is we have to find the sum of resistance. And remember, there's something called internal and external resistance that must always be there. Please note that there has been a change of names. To find the U-value, you take the reverse of sum of resistance, and then you just miss to do heat transmission, and that is the reverse of sum of resistance times temperature difference. Please note that there's units on the gift tags. As we always do, we start with writing out the problem, and in this case we also remember to sketch a model of the construction. Because it's a single layer, the model looks like this. What you also must remember is we have something that we call internal temperature, which is 20 degrees Celsius, and external temperature, which is minus 12 degrees Celsius. We also state what the internal resistance is, and that is 0.13 square meter times Kelvin over watts, and the same with the external resistance being 0.04. Those are constants. Please note the direction of the heat flow, from hotter to colder. We must also write off the thickness for the glass, and that was 2 mm, and the 2 mm was go to meter, so it's 2 times 10 to the power of minus 3 meter. Now we have to look up the thermal conductivity for glass, and thermal conductivity is a material constant, and it has the symbol lambda. To find the value for the thermal conductivity for glass, we look it up in a table. This table is from hyperphysics. As always, when we look values up in tables, be aware of the unit. We use this one because that one holds the SI unit. And the value for glass ordinary is 0.8. Let's highlight it and set it in the exercise. I have filled in the value for lambda glass. And now I have to do the resistance for the glass, which is thickness divided by thermal conductivity. I write the value out for the glass, and that was 2 times 10 to the power of minus 3 meter. And then I divide with 0.8 watts over meter times Kelvin. And that is the same as 3.13 times 10 to the power of minus 3 meters squared times Kelvin over watts. Now I have to find the sum of resistance, and that is equal to internal resistance plus resistance of the glass plus external resistance. Always remember to write up the equation with symbols, and then afterwards you fill in with numbers. Fill in the value for the resistance, and internal resistance has a value of 0.13. The resistance for the glass was 3.13 times 10 to the power of minus 3. And finally, external resistance is 0.04. Close the parenthesis and remember the unit, and that is meter squared times Kelvin over watts. So the sum of R becomes 0.173 meters squared times Kelvin over watts. Now we can find the U value, and we remember that the U value was 1 divided by sum of R. and let's see what we get. U is equal to 1 divided by 0.173 meter squared times Kelvin over watts, and this is the same as 5.8 watts divided by square meter times Kelvin. Is this U value a good U value? No, it's not, because the higher the U value, the more heat is escaping. Now we only miss to find heat transmission per area, and heat transmission per area takes the symbol capital Phi divided by area, and that is equal to U value times temperature difference. So capital Phi divided by A is 5.8 watts over square meter times Kelvin times the difference in temperature, and that is 32, and the unit is Kelvin. So what we get is we get 185.6 watts per square meter.